Okay, in this video I add the NKS key or the radar key to the knife. This key opens any disabled toilet in the UK. I think it's a really cool feature. I design it, get it cut out, sand it and polish it in this video. Alright, so how do we shrink this down to fit the knife a bit better? We don't really care about this dimension, obviously, but thinning it down is important. So let's see where we're starting off. So obviously the widest point, we don't care about the, I've learned this is called the bow. We don't care about the bow, we care about the business end. The collar is obviously the widest point, which is about 7.1, 7.2, depending on the key. It's also not totally round. Okay, it's pretty round. I guess this one's about 7.2, 7.1 rather. We don't particularly care about the thickness of the actual, I don't really know what this is going to be called, this thing, the actual, I'll have to look up the terminology for keys, but the little flag, I'm going to call it for the purposes of this section. So the little flag part, which actually, interacts with the levers in the mortise lock, is quite thin. It's only 2.3. So obviously it'll be a mate. That's the, you could probably operate the key with a thinner one even still, but really that's not the constraint. The constraint is the diameter of this part of the key, which is here about 5.4, 5.5. Yeah, 5.4 at its minimum. What is it the other side? About 5.35. Yeah, it's about 5.4. That's quite thick. To give you an idea, I think the thickest layer in the knife is the magnifying glass layer itself. And the width of the tool there, or let's go with the inside width between the what are they called, liners, is about 2.9. Thickness of the tool is 2.6. It's actually kind of surprising. I think that's a thinned region on the magnifying glass there. The bit that's actually riding on the liners, I think, is a bit thicker. So yeah, about 2.8 in there. Is that the same at the other end? Should be, I guess. Yeah, 2.8, 2.9, 2.8, 2.85 maybe. So yeah, that's, I think, the thickest layer on this knife. They're all much of a muchness. So obviously it'd be great to be able to get down to 2.8, but that's nowhere near achievable. What is achievable? Well, let's have a look at how the key actually works. So what are the features here? Obviously you'll notice it's mirror symmetric because it has to engage the lock from both sides and unlock it from both sides. So that's that. It's got this shoulder here, this collar, and that butts up to the kind of lock opening here, because obviously those levers have got this flag has got to go in, and these little features on it have to line up with the levers. So obviously the depth has to be a positive stop there to get the right relationship in the longitudinal axis. So we're going to need some kind of a collar, but we're not going to need it all the way around the circumference of the shaft, as long as it can engage, because we've got sort of, let's say, 80% of the circumference, or 75% of the circumference maybe, present on the barrel here, or the whatever we're going to call that, the opening of the lock. Yeah, a partial collar will be fine just to establish a good positive stop there, and so hopefully we can just have that on the upper plane of the key, and then on the side of the key we can flatten off that collar. So yeah, I don't anticipate any problems with that. So can we go thinner? Well, probably, because obviously the key needs to rotate, and it needs to be stable about its axis of rotation. And the way that is guaranteed is that the round profile of the key obviously rides on this surface here, so like kind of makes a little journal on that surface. And of course, you can get away with a partial shaft. So you could say take a round shaft, flatten in the sides a little way. It's still going to rotate in a circular hole. That's obviously complicated slightly by the fact that the hole has a big gap in it at the bottom, so that will obviously, there'll be a limit there. So yeah, if we just kind of think about that, just kind of sketch that out. If this is kind of your barrel here, and there's actually a section missing here at the bottom. I've kind of maybe exaggerated the width of that, just give you an idea. The key, let's say it's round for that portion, and it's round for this portion, but then we shrink in the sides a little way. What are the limits on that? Well, so if that's the little flag part of the key down there, that's going to work fine as we shrink that in up to a critical point, which I think is going to be when if we bring this corner in and it comes inside this wall here. Obviously, then there's a possibility for the key to start to drop down into the slots of the shaft of the key, because it's now narrower than this opening here. It could sort of slot down into that gap, but as long as there's a little bit of margin there, so as long as there's, say, I don't know, 0.5 millimeter there or 1 millimeter, I reckon that should be okay. And obviously bear in mind that the other side of the thing, you've got kind of a seesaw going on. As this side tries to drop down, well, its corresponding side here is hitting the upper surface of the opening on the back side, so obviously that's going to stabilize it. So it's hard to know really what I can get away with until I try it, really. So I'm going to take one of these keys, and I'm going to machine down the sides, test it, machine off a bit more in the mill, and see what we can get away with, really. All right, we're over at the lathe in milling mode. I've got the key here mounted onto the vertical slide. I've got a 12mm end mill in the collet chuck, and I'm going to machine off a bit of the side of the key. It's called the pin, I've learned, that particular part of the key, which rides in the barrel of the lock. I'm also, obviously, in doing that, I'm going to machine off some of the collar, the stop collar as well, all of the side of it. I'm going to take, currently the pin is 5.4mm diameter. I reckon 4.5 is going to be pretty safe, so I'm going to go down to 4.5, so that's 0.45mm off either side. So I'm going to use a DTI to measure the travel as I go, but first I'll just machine off that collar just to see how everything goes, and then I'll touch off on the side of the pin and then start measuring. So that's just the collar starting to be cut away there. yeah, we're already touching the side of the key. Crikey. The side of the pin. Yeah, just grazed the side of the pin. I put a little bit of Sharpie on the side there, just so I can see where I touched it. Only barely grazed it there, so yeah, no harm done. So I'll set up a DTI. Right, okay, that's a better setup. I've got the DTI probing the actual saddle now, so that it's not measuring a surface that's moving sideways. Of course, I got that zeroed. Let's just check that. Okay, yeah, zero that. Okay, right, that's pretty reasonably repeatable, within 10 microns or so. So I reckon we've already taken off about 0.05, so I'm going to take off 0.4 now. So I'm going to back it off to 0.1, move out at the end of the cut and start that off. So this should be a more or less a... Ooh, shit, what's going on? Oh, Christ. Try not to destroy everything. Oh, I see. I just clipped the copper. Saddle because it's moving around a bit. Right, so here's the thinned down key after the first thinning, and it's at 4.7 at the moment. I was shooting for 4.5, so, but I kind of lost track halfway through, so I stopped to measure and did a little bit short, but it's nice and symmetric still. Each side is removed. I've taken the same amount of material off. You can see there's a flat on each side, and they're the same width, so they're central on the key axis. And yeah, I mean, kind of fairly unsurprisingly, it still works fine. So the question is, as we keep thinning this, what's the limit case? Where do things start falling over? My guess is, as I mentioned earlier, when the width gets narrower than the sort of slot part of the keyway. But who knows? I might be wrong, because obviously each end is riding on the sort of crest of the cylindrical part of the keyway. So yeah, that's obviously keeping things central. So I'll just keep thinning it until it stops working, and then we'll know, won't we? So it's at 5.7, at 4.7. I'm going to try a 4.3 now because although that's not very much material off, it is kind of the first width at which it would fit nicely into the Swiss Army knives at the moment, or like a kind of typical Swiss Army knife slots. Let's say if I move that out of the way, for example, that slot opening there is about 4.5, so that doesn't quite fit in at the moment. It's 4.7, but yeah, I'm going to try 4.4 or 4.3 maybe. See how that feels. Of course, thinner would be better, but at least that would be, I think, acceptable, even if we only get to 4.3. So let's try that. 4.3 it is. Okay, so here's the key with another 0.4 taken off, so we should be at 4.3. Our survey says 4.35, 4.34, not bad. Let's deburr it. Don't want to fill the lock up with the bits of brass swarf if we can avoid it. Doesn't have to be super perfect right now because we're going to take more material off. So. Yeah. I'll do. So I reckon this is still going to work fine. Our survey says, yeah, still works fine. So it's easy to put it in. Even with a bit of pressure, it doesn't want to kind of foul or anything. So that's good. And this should fit into the into that little gap in the knife quite nicely as well. Yeah, so there you go. That starts to tuck in there now. Not that, you know, that's particularly meaningful because obviously this is sort of somewhat arbitrary. And in the, obviously we're going to add a layer for this, and we get to decide how thick that layer is, and obviously that's what we're trying to determine with all these tests, is how thin we can get away with. But clearly that's already looking practical. You know, you can imagine that folding down and stowing away in that little gap there. Well, it doesn't quite work because of the shape of the liners and stuff, but yeah, you could make that work. So that's not too bad. Sweet. Definitely fits. I'll argue with that. Yeah, that's a good way of showing it, yeah. So it tucks in there quite well. So what next? I think we can, well, obviously remove some more material. How much? Yeah, I think we definitely want the key to be wider than the slot part of the keyway, because otherwise, when you put the key in, there's a pretty good chance you're just going to miss the hole and get the tip of the pin in the slot, and then it's, yeah, that's no good. So unfortunately, you know, in a sane world, you would know what industrial standard this is designed to, and you would be able to get the geometry of the keyway with tolerances specified, and then we would know what's the worst case, you know, what's the widest that is allowed to be by the standard. But of course, the world doesn't work that way most of the time, so we are in the dark. So yeah, it's a bit of a guessing game really, but let's go, I don't know, what, half a mil wider than that? So I've measured that at 2.9. So let's call that 3. So should we get under to 3.5? Should we really remove some material here? Why not? The width of the this is called the bit, by the way, the bit with the actual coding on it. The bit is 2.3. So 3.5 would be what? That would look like, yeah, it's getting pretty thin. Just as a reference, how thin is that? That's less than 3.8. Yeah. This gap here. Yeah, 2.9. So 3.5. Should we try it? Why not? So just eyeball it again, just see what it feels like. Yeah, I mean, when you look at it like this, it's not that drastic. We could even be more drastic, I think. I reckon 3.5 is a good target. Let's do it. Okay, this is great. We are at 3.5 on the thickness of the thickest part now, and the pin, as it's called, and it still works perfectly. It goes in nice and positively. There's no kind of chance that you might accidentally get it in the slot. It's nice and positive in the lock, and it works fine. Both directions, no problem. It's not the nicest feeling lock, but it feels no worse with a brand new key. Actually, this one feels worse than the thinned down one. So that's fantastic. I'm happy with that. Of course, what I'm trying to do is minimize the amount of additional thickness that I add to the actual knife. So I haven't really explained it very well yet, but you can probably see the knife is obviously a stack of layers. In Swiss Army knife lingo, a layer is one set of tools, and it's and it obviously sits between two aluminium plates, which are called liners. I'm not sure if the outer ones are called liners or whether people call them that, but they're all doing the same thing. These liner plates are there to support the pins against the side loads, and obviously take up the side loads of the springs, because the back springs are all under quite a lot of tension, and they're sort of applying stresses along the axis of the knife mainly, and a little bit across the axis of the knife as well. So yeah, those forces are all taken up in these plates. Interestingly, they're not all the same thickness. Mostly they're 0.7 mil, but this knife has one which is 1 mil, and it's the one which is in the layer with the magnifying glass and the Phillips screwdriver. And I have a feeling that's because the Phillips screwdriver has the highest spring pressure in the knife. It's got two very sharp detents, and they're quite stiff. I'm not certain that that's the reason, but I can't think of any other reason that would be the case. Most of the other blades have a more gentle increase in spring load, even the knife blade, although that does have a pretty stiff, as you would hope, a pretty stiff retaining opening force, which is, yeah, pretty interesting. I'm not sure why then that's the case. It's also the central plate in the knife, but I don't. Perhaps that's another reason. It could be that one's thicker. It's not the case on the companion. All of those are the same thickness, I'm pretty sure. Yeah, they're all 0.7. So yeah, that's a slight mystery to me. It's tempting, of course, to thin that down because we're adding material and adding another whole layer, and it would be good to keep it as thin as possible. But for the sake of 0.3 mil, I think I won't mess with the design. I think I'll leave that as is. So one important detail about the liners, they're all different shapes. So the outer liners are more or less the same shape as the scale, but the inner ones have various sort of relieved areas. So you can see that has quite a deep relief there. This other one has a relief of a different shape, and that's there to provide clearance for some of the tools. So, for example, and also to allow you to sort of get in there and grab hold of the opening features, like the for example, the thumb slot on the. I'm thinking specifically about the thumb slot on the scissors. That's sort of, that would be quite hard to get to if the plate, if the scale came all the way up to the same width as the rest of the knife. So yeah, so we can make use of that, obviously, because that gives us some additional space inside to accommodate the thicker part of this this tool. So we know that the pin, I'm happy with 3.5 mil as the width of the pin section, but we can thin down the actual shaft because it's going to be stainless steel. We can make it a little bit wide and we can make it flat, and that's going to be amply strong, and it can be thinner, which means that the actual, because obviously the thing that sets the amount of additional knife thickness is not what happens in the middle, it's what happens where these pins are. So we want to so for example, this is a good example. This tool here, the Phillips screwdriver, you can see that the tip of the screwdriver is actually wider than the layer thickness. So the layer thickness is, in this case, I think 2.8. Yeah, 2.8, 2.85. And the tip of the actual tool is about 4 mil. And the way that works out, obviously, is they make use of the relief slots in the liners to essentially create additional thickness. So if you've got a pair of liners like this, of course you've got a certain amount of thickness in the gap between them, but then the tool can occupy the additional width of the thickness of the two plates added onto that inner gap width. I hope I'm making sense. So what I'm trying to say is we've now determined the widest part of the tool. But the question is, how thin can we make the thinnest part of the tool? And that defines our layer height, and it defines the pin length, the rivet length, and so on. I mean, not that we really have to worry about the rivet length as long as they're long enough, but we can, adapt them to fit. But it would be good to know how thick the knife's going to be, and also, obviously, we need to know how we're going to machine the part or make the part. We're going to fabricate it out of sheet and then maybe weld something on or solder something on, braze something on to thicken up the thicker region, or we're going to probably machine it all out of one piece, most likely. So yes, that's that. So it's quite nice that if we keep this 1mm thick plate, I don't really feel like messing with it. We can use that 1 mil thick thickness to accommodate the thick part of the key, and then we just need to add one more liner of our own to accommodate the other side of the layer with the key in between. Thick as mud, clear as mud, right? So here's the design of the key. This is in FreeCAD. You can see the width of the pin at the end here. This is 3.5mm thick, as we determined by thinning down the brass key. And the shaft is 2.5mm thick. Setting it to 2.5 allows me to use the same back spring that's used in the scissors layer, and I can scavenge one from the companion that I dismantled to steal the box tool and nail file. So that could be the source of parts. You can see this is pretty challenging to machine. It's got this cylindrical section on the end, cylindrical region around here, and this flat bit as well, and then also these undercuts. So if I'm going to make this myself, I'm going to have to probably file bits of this, because obviously you can't get cutting tools into all of these areas. So yeah, it's going to be pretty challenging, particularly on a 2-axis lathe. I can obviously put it in milling mode and maybe put a rotary axis on as well, so I can get kind of 4 axes. But really you'd want a 5-axis machine to do this in a sane way. Yeah, not easy. Probably climb milling, that's a bad idea. Okay, that works. Alright, so this is where we are at so far. So basically I've machined this curved surface, this curved surface, this collar very roughly, and the tab, whatever that's called. I think it's called the bit. I think this is also called the bitting. I'm not sure. So yeah, some good things and some less good things. Probably no bad things, but yeah. So this is spot on size. This is a nice sort of portion of a cylinder, and it's pretty much 5.5 as intended. So that's good. The machining went pretty well. The axis of this part of the key, the actual kind of mechanically functional part of the key, is ever so slightly off the axis of the sort of shank, which is the axis of the fixture block on the rotary table. I think that's just to do with the inaccuracies probably in the rotary table itself, because it's pretty rough. So I was having a hard time making this part on the lathe. There's a lot to it, particularly dealing with this undercut here. Yes, I could file that. Getting the rotary axis of the key aligned on the rotation axis of the table, and getting that the rotary table and getting that all lined up with respect to the lathe was proving tricky. Cutting out the bitting for the key was going to be tricky. Yeah, I basically chickened out, so I got it CNC machined. And this is from Jomic in the UK, Geomiq, not sponsored. They did a phenomenal job. It was about 100 quid, which I'm very happy with. They did they got it's all perfectly within tolerance. I spec'd plus minus 100 microns all over. They did that no problem. I'm sure I could have asked for tighter tolerances had I wanted them. And they even managed this impossible geometry here. They did this undercut. Bring it in a bit closer to the camera so you can see what they managed to do there. So they managed that undercut, and I was assuming I would send off the file, and I was assuming they would get back to me about this undercut and say, what do you want to do about it? Because it can't be cut, obviously, on a CNC mill. It has to be EDM'd or something, something ridiculous like that to get right in there. And even then, EDM wouldn't give you that curved surface in there. So, how the hell are they going to do that? And that curved surface in there is important for the way the key operates in the lock. But, yeah, obviously you would want to make it in two parts and then weld it together or something industrially. And that's exactly what they did. They TIG welded it together. I can tell that because there are some absolutely minute microscopic gas bubbles in the weld that I could see just here and there at one end under the microscope. Nothing that would at all impede the quality of the work. They did a really good job. And yeah, obviously they made it in two parts, welded together without even batting an eyelid, without charging me much for it. And did the whole job for 100 quid, which I thought was very reasonable. So anyway, the geometry of the part, you can see it's thinned down in this section, which is to keep the tool as thin as possible. The key is only 2.5 mil thick. So when you add 0.5 mil for one extra liner, that adds 3 mil to the thickness of the whole knife, which I'm very happy with, because obviously each tool needs to add one liner between tools. So that'll be 3 mil of extra thickness. 0.5 mil for the liner, 2.5 mil for the part, for the key, the shank, and then the actual key body itself is a bit thicker. But the idea is that rests in cutouts between two liners. So this part is, I think, 3.5 mil. Yeah, 3.5 mil. And that fits between two liners. So essentially 0.5 mil off, and you're back down to 2.5 for the shank. So yeah, that's that. So I'm really happy with that, but it doesn't quite fit in the lock yet. So I'm going to have to do a small amount of filing. Obviously, I should have. Well, it's very hard to measure. Yeah, I probably could have been I could have asked for tighter tolerances, and I could have potentially measured the lock slightly better. But yeah, I just had to file off maybe 50 microns here and there off the tip to get it to fit in the lock. So yeah, I think the curved top profile of the key isn't quite right. I think it's at the upper end of its tolerance. It's absolutely in fact it's slightly over, 20 microns over. I specified it 5.5 plus or minus 0.1, and it's maybe 20 microns over according to these calipers. Actually, maybe it's even over that. So maybe this actually isn't in tolerance, this part. Yeah, that's not particularly impressive, is it? 0.1 mil over. So I'm going to use some engineer's marking glue to figure out exactly how it's going to fit in or not fit in the lock. Because at the moment, the key goes in straight, but the very tip of it should fit in sideways. Because there's I think that's about a 5.5 or a 5.6. If I get a 5.6 mil drill bit, I think that fits in. That fits in, and that's the upper end of the tolerance band. I think 5.7 doesn't fit. I don't have any gauge pins, but a 5.7 doesn't fit, and a 5.6 does. So we'll call that 5.6. See what this drill bit actually measures. Yeah, 30 microns under 5.6, so call that 5.6. So 5.6 fits. Poor man's gauge pin. So yeah, I don't even need marking glue. I think we can probably see that's on those crests there. 5.6 that side, and 5.7 that side. So I think, although it's hard to know exactly where the high spots are. So let's see if this is going to work. We'll try some marking glue. I never actually use this stuff. I've had it kicking about for ages, so let's give it a go. Can't even open the tin because it's been seeping ominously in the corner of my measurement drawer for some time. So yeah, God, this stuff's horrible. It covers absolutely everything in blue. You've got blue on you. So I think I forgot to press record there, but I've been using some marking glue, and I found some high spots on the on the corners of this radius. So I'm just giving them a bit of abuse with this file. This is a very, very light cutting file, I think. Is it number 4 or something? Really, really fine-toothed velour, nice Swiss file with a safety edge, which I'm riding up against the key collar. So I realised I actually got a radius gauge here, which I can hold up to the key with some light behind it. And yeah, the radius is not accurate on this top surface. So we're getting there now. The key goes into the lock, and it wants to rotate, but it's still a bit tight, so I wouldn't want to rely on this. I think different locks are going to have different tolerances, and I think I'm going to make that a little bit larger. But this does seem to want to work. Right, well, the hoof tools heat treating, I'm going to polish up the key. So the key was delivered from Jomic with a brush finish. I'm going to take it up to a mirror finish, so I'm going to go up through the grits and then buff it on the polishing wheel. So first off I have to determine what finish they've put on it. It looks like about 600 grit or something, it's quite fine. So let's start there. Let's try some 800 for a start. Yeah, that might be a bad start actually. That's after 800 grit. That's gone pretty well. I'm going to keep going through 800 grit on all the other surfaces and then get down to 1200. And here I'm buffing with Dialux green buffing compound on a Swansdown mop. And here's the finished key. It's covered in fingerprints, but you get the idea. It's got a beautiful mirror polish and it opens the lock beautifully. Okay, if you made it this far, thanks very much for watching, and please comment to tell me how I can improve these videos. I'm trying to learn how to get better at video creation, so all comments welcome. Thanks a lot.